Now I have to restart again. Let me start by saying that certainly there is still a lot of knowledge and experience to be acquired, particularly on how to obtain the required data and apply the analytical procedures and models, scenarios, and on how to apply the lessons learned to support decision-making processes in risk management associated to slope and stability hazards. Let me start by admitting that at present, we must face several complex challenges when required to unravel the relationship of slope and stability hazard and anthropogenic global warming. First, healthy attitude is to keep a foot on the rational grounds based on science and objective realities. And I say this because I have found a significant degree of confusion on what really is climate change, the differences with anthropogenic global warming, climate variability, and the way they affect slopes. There is currently a flood of information, some veracious, other confusing, many full of myths, doubtful science and communication bias. Currently, misinformation abounds, full of half-truths, exaggerations, fake news, and this harms significantly the cause of risk management. But since developing countries have to tackle the harsh realities of not disposing of unlimited resources, an order of priorities of action is required. Facing the consequences of anthropogenic global warming is only possible if its causes, variables, and features are measured. The most important priority is to acquire the skills and data to be able to perform robust probabilistic risk models of anthropogenic global warming. They must be dynamic in space and time with adequate scales for national, regional, municipal, and project management. There is another urgent priority, fostering the spread of objective information. First step would be to provide a quick reminder of the principles of risk and risk assessment in general. It is important to stress that in these complex current times, at the beginning of the third millennium, integrated risk management must focus on all kinds of hazards, considering that clearly or not, most of them are interlinked somehow. Consider that as it happens most of the time, while trying to produce classifications, the list of items are almost never complete. Also, it becomes necessary to schematize, sometimes to the extreme, and that relationships and boundaries in classifications are often fuzzy. So let's start by mentioning the anthropogenic hazards and those associated to the environmental features, such as pollution, land degradation, anthropogenic global warming by itself, solid, liquid and gas waste and residues, industrial accidents, spills, fire, explosion, and nuclear accidents. We can also have socioeconomic hazards such as poverty and mass migrations, health hazards such as famine, pandemia, and epidemics, and occupational and health and safety issues. Security hazards associated to armed conflicts, cyber attacks, social conflicts, vandalism, terrorism, and human stampedes. And on the natural hazard side, we have the hydrometeorological and climate hazards, such as climate variability and change, cyclones, drought, floods, tornadoes, sand and dust storms, and sea level rise. We also have the internal geodynamic hazards, such as seismicity and volcanism. And then we have the ones that we are focusing on today, external geodynamic hazards, such as erosion, slope instability in the landslides and rockfalls, torrential debris flows. And then it is quite clear that anthropogenic and natural hazards are interlinked, as I said before. So in terms of hazards, land degradation, anthropogenic global warming can enhance the effects on all the natural hazards. Or, for example, in case of the anthropogenic hazards, we can have an enhancement on the vulnerability parameters of risk. On the other hand, let's continue with a brief reminder of the differences between weather, climate, variability, climate change, and anthropogenic global warming, and their respective temporal and spatial features upon which hydrometeorological and climate processes evolve. For instance, weather is defined as the representation of the synoptics of current and the very short-term meteorological features. Here we're talking about today, a week, 10 days. So we just take our cell phone and we see our favorite app application and check on what's going on in the right now, the next week or the next 10 days in terms of weather. On the other hand, we have variability, which is the description of the dispersion of hydrometeorological and climate processes in the middle term. In here, we are talking about interseasonal, interannual, or up to 20 to 50 years in that dispersion on the regional and global scales, and the description of the episodes of El Niño, La Niña, southern oscillation, or the position of the intertropical convergence zone, the monsoons, polar thrust and vortex, tropical cyclones, oceanic circulation. Picture below, and the footnote of the picture described that in 3 days, Limón received all of May's rainfall. Limón is the Caribbean port of Costa Rica. So it means that in 3 days, in relation to the statistical and historic time series of rain gauge in that site, that particular May, doesn't matter real year, Limón received in 3 days what was supposed to be received and precipitated in a full month. That is what variability is all about. And thirdly, we have climate change, which describes the trends to the long or to the very long terms. Here we're talking about millennia, millions of years, and so on. Let's remember that our atmosphere was mainly produced by volcanic activity and some cosmic accretion. But weather is also, and climate are also influenced by plate tectonics, and mostly by the Milankovitch cycles, which describe the variations in warming and cooling alternations and episodes due to solar radiation. These Milankovitch cycles derive from the influence of several astronomical circumstances of our planet, such as, for example, the inclination and variations of the obliquity of the axis of rotation of our planet, or the eccentricity of the orbit of our planet around the sun, which is not a circle, is an ellipse. So we are sometimes closer, receiving more solar radiation, and sometimes we are farther away, so we receive less radiation. And a combination of this and some other factors describe what we call the precession, which is the explanation of why we do have seasons in both hemispheres, but with variations between a year or so in between. So this is for the natural part of climate change. But then we have the anthropogenic part, which comes from the excess of anthropogenic emissions of greenhouse gases, vapors, and particles. What is producing what we call the anthropogenic-driven global warming, because mostly they warm the atmosphere. Even if some of these gases, vapors, and particles, some of them cool the atmosphere, most of them warm it and keep and drive the warming of the atmosphere for longer periods. So the summation of these causes, effects, and impacts is what we are now calling climate change. But let's not forget, and I will remind this factor further on, that climate change is not only produced by human activity. So the combination of all these features are being observed and surveilled, and this allows us to develop the methodologies of analysis of space and time distribution of the variations through time. And then this allows us also to prepare predictions, projections, models, scenarios, and downscale from the global to the regional to the local circumstances. So this is a way that we have to assess positive and negative effects and impacts, and risk management procedures to assess and to try to orient and assist decision-making processes. As of what slope and stability hazards are concerned, as part of the external geodynamic processes that focus our attention today, the classification used here has been adapted to better fit the conditions usually found in tropical and subtropical areas. I have used the classifications proposed by several authors, and I take the opportunity to manifest my appreciation for the excellent previous work done by Professors Varn, Cruden, Kostra, Hangre, Leroy, and Picarelli. They have been the cornerstones of our knowledge in the field of slope and stability, classification, and analysis. In our case, as we well know, the most common types and motion of unstable masses derive from their main features associated to their composition by blocks and fragments of rocks, mixtures of them with biomass, ice and snow, and or soil, such as, and among others, what we call free fall, fragmentation and propagation, tilt, topple, fragmentation and propagation, slides that could be either planar, rotational, prismatic, or irregular, lateral separation and spread, complex and composite systems, river course damming by slope and stability and their ensuing effects, flow produced by debris, and avalanche produced by snow and ice. The positional processes derived from slope and stability and flow, and slope and stability in anthropogenic deposits. And as it has been thoroughly documented, the presence of or absence of water by means of the degree of saturation, the composition, and geomorphic features of slope terrains govern the velocity by which masses move, sometimes also triggered by earthquakes and human activity. The following diagram shows some general and schematic samples observed in areas where I have had the opportunity to work. As it is, the water content may vary from dry to nearly dry up to nearly to fully saturated materials. As composition is a concern, it can vary from pure soil masses to pure rock block masses and practically everything in between. And this regulates the velocity that could be just from creep, very slow velocities to very rapid. And here's a very brief and very schematic summary of the processes that I have been able to describe throughout my career. Rock block separation, tilting, toppling, and fall and flow, fragmented debris and soil block separation, tilting, toppling, and falling, glaciers, ice and snow, dunes and borehans, AA lava flows, translational mega slides, soil creep solifluction, rock slides, lateral spread and separation of terrains, rock block flow, earthquake soil liquefaction, avalanches of snow, torrential debris flows and lahars, and hyperconcentrated debris flows. All previous notions must be incorporated along the line to perform a proper assessment of risk, for which I dare offer in a simplified reminder as described by means of the log-Axenes function, which is the number of times per year that events might occur and cause an equal or higher specific value of losses. The annual frequency of losses can be described by the Axenes rate calculated by means of the total probability theory as follows, where CP describes the Axenes rate of the loss P, AF of the event I is the annual frequency of occurrence of the event I, B is the loss cost to elements exposed to be summed at the ensemble of all stochastic scenarios. This is the probability that the loss will be higher than P, is the materialization of the ith event. And TR is the return period of the loss P, which means is the inverse of the exodus rate CP. If we come back to the hypothesis that climate change, meaning anthropogenic global warming in this case, is in some areas driving an evolution to more intense hydrometeorological hazards, we must adjust, at least hypothetically, the way to assess risk derived from slope instability hazards, as also evolving accordingly along a specific temporal horizon. This notion requires differentiating the long-term effects of anthropogenic global warming from the natural variability of extreme hydrometeorological processes and from those associated to natural climate change. And we have the variability of the extreme hydrometeorological events, natural climate change, and the anthropogenic global warming. Then global warmings are, in this case, the most important analytical tool under downscaling procedures. But in such a case, the current baseline can be set to assess the intensification of climate variability extreme effects and the temporal evolution of hazards and vulnerability. So the evolution of hazards and the change in hazards, we will call it delta hazards, and very importantly, the evolution of vulnerability to assess risk, we will call it the delta vulnerability. So we can assess the negative impacts, and then we can assess risk derived from anthropogenic global warming and the changes in slope stability hazard to define risk management processes, including adaptation to anthropogenic global warming, and to assist decision-making processes. Therefore, the development of a prognosis for understanding the increment of slope instability hazards to assist decision-making can be attempted. As an example, let's consider the current conditions of risk associated to any slope instability situation and tackle the evolution of risk under the influence of anthropogenic global warming and an increase in slope instability hazards. Before that, we must take into account that currently most damage, and this is very important, and losses caused by slope instability come from human vulnerability associated to climate variability rather than climate change or anthropogenic global warming by itself. So what analyzing the evolution of risk through time, any scenario must integrate the potential incidence of anthropogenic global warming for both hazards and vulnerability along a specific horizon. Therefore, most certainly changes on risk will be progressive and not sudden. So we can describe the change in risk by the change in hazard through time and the change in vulnerability described by the change in damage potential through time. So this is what we call the relationship of delta risk as the combination or convolution of the delta hazard and delta vulnerability, where R is risk, H is hazard derived of slope instability, delta H is changing H along a temporal horizon, delta T, V is the vulnerability, delta D is the change in potential damage and losses during delta T. And therefore, we can create three main scenarios that may become possible. The first one is that risk could remain unchanged. The change in risk is zero. Or even in some areas, the change in risk could decrease. And then risk can increase, can become larger than zero. And this is the scenario that we will keep from now on throughout this presentation. So this new risk must be defined separately and then aggregated to that already been caused by climate variability. Analyzing risk under the incidence of anthropogenic global warming, considering the evolution of hazards and vulnerability after a temporal horizon, is not an easy task and requires specialized modeling and probabilistic skills. Requires teamwork, I don't know anybody who could perform by himself a single risk analysis. It requires a team. Then, as we have seen, the deltas describe the evolutionary changes of risk represented by differential equations that we have just enunciated. Hazards and vulnerability will add to their magnitudes by their evolution through time. So risk will change because from hazard, the current hazard level, due in this case to climate variability and the current levels of slope and stability hazard, will change driven by anthropogenic global warming through time and convoluted or combined with the change of vulnerability from the current change, from the current levels of vulnerability associated to climate variability, and then further vulnerability aggregated by the causes driven by anthropogenic global warming through time. As graphically seen, the current slope and stability hazard might be driven towards an increase of its occurrence as a random distribution of an aleatoric variable describing the relationship or the probability of exceedance of the hazard versus its intensity. This means that from the current position and level of the hazard described by this curve, anthropogenic global warming will drive this curve upwards, increasing the probability of exceedance and the hazard intensity eventually. The same hypothesis may apply to vulnerability as a random distribution of an aleatoric variable describing the probability of exceedance of damages versus the intensity of the hazard. It must be considered that there is a normal increase of vulnerability independent from anthropogenic global warming derived from an increment of exposure and fragility typical in our developing world. We have here the current distribution of vulnerability, probability of exceedance versus the intensity of the hazard, and the growth of vulnerability just by itself through time, because there is an increment of the demographic characteristics, the expansion of urban areas, infrastructure work, and the increment of exposure to natural hazards. Anthropogenic global warming will cause an additional increase of vulnerability through the reduction of resilience, environmental degradation, and an excess increase even in exposure. And this is what is actually being produced in here. So vulnerability increases by two-fold. One, the normal increment of vulnerability, and secondly, the one that is driven by anthropogenic global warming through, for example, a reduction of resilience eventually of the population and an increased exposure to the new conditions of climate variability. So, therefore, the distribution of risk is also subject to a change. Damage distributions of events similar return period, such as the ones are exposed here, a 25-year and 50-year return period, will increase, driven up by the anthropogenic global warming parameters. If all other factors remain constant, it is also possible to say that if we keep the same return periods that we're analyzing, the return periods actually will be reduced as to produce the same levels of damage and risk. In practical terms, what possible scenarios may feed the analysis of risk derived of anthropogenic global warming-driven slope and stability hazards? What the impacts of the increased extreme events of the new climate variability will occur after a temporal horizon of, let's say, 30, 50, or 100 years from now. For example, the increased atmospheric and oceanic temperature may produce an increase in the number of warmer days, heat waves, and thermal stress. And this will be the cause of the deterioration of human, animal, vegetable quality of life, impacts to biodiversity and genetic banks. Let's remember we're talking about here about risk, not only about hazards. It means we have to incorporate criteria to assess vulnerability as well. So we could have in some areas a lesser amount of rainfall, which might generate a deficit of hydric balance. And this might cause the reduction of hydric resources availability and moisture stress, an increased drought intensity and frequency, and landslide degradation, land degradation and deterioration. But on the other hand, we could have an increased precipitation in multidimensional ratios in other areas, which might create an increased intensity, duration, and frequency of extreme rainfall events. And this will be the cause for an increased slope instability, among other problems, and an increased weathering, runoff, erosion, fluvial flooding intensity. The sea level rise will be at the origin of an increased coastal and littoral submersion and an increased erosion, flooding in coastal and wetland and lake shores. Intensification of extreme windstorms, of cyclonic or trade wind systems will be the cause of increased waves, gales, squalls, tempests, and surges. And changes in sanitary conditions will be the cause of an increased spread of vectorial diseases, plagues, epidemics, and pandemics, which will cause effects and impacts over the population, agriculture, livestock, lands, and ecosystems. So this is a very summarized and schematized scenario building procedure that should be taken into account while assessing risk associated to anthropogenic global warming. So being a bit more specific, on the external geodynamic processes and the way they might evolve under anthropogenic global warming, what may happen if sea level rises and if there is a sustained alteration of the hydric balances. A possible scenario building process to incorporate risk management derived from slope and stability hazards and the influence of anthropogenic global warming could look like this. So, coming from the sea level rise, we could have coastal cliff, sea, wetland, and lakeshore erosion, and the enhancement of the effects of tides, storm surges, and tsunami. If we analyze the multidimensional variations of intensity, duration, and frequency relationships, we could have, on one hand, a lesser exposure to intensity, duration, frequency of rainfall and river discharges, and then a reduced slope, cliff, road cut, and field instability and debris flow activity. But if there is a higher exposure to intensity, duration, frequency of rainfall and river discharges, combined with sea level rise, we will have an increased slope, cliff, road cut, and field instability and debris flow activity. So this is the way to analyze and assess the positive and negative effects and impacts. And then to produce risk management procedures, including adaptation, to assist decision-making processes. The root for all these changes might come because of the way the rainfall patterns may evolve through time. Let's remember that we are only assuming for now a scenario where the multidimensional parameters of IDF functions will increase. Therefore, in a specific region, we must start by separating climate variability and anthropogenic global warming influences, quantify spatially and temporally. And the first step must be taken to define hydrological and hydric balance parameters and the characteristics of the extreme event scenarios. Meaning by this, how rainfall intensity, duration, and frequency may be modified, driven after a temporal horizon. The return period of a damaging scenario will increase IDF, but essentially will decrease by itself. We will require less return periods, lower return periods, to obtain the same type of intensity, duration, and frequency due to the anthropogenic global warming. In addition, of 5 to 10% when we do dispose of an IDF function might serve as a proxy to simulate the increasing effects of anthropogenic global warming until data and adequate, robust, probabilistic stochastic models become available. Then comes an attempt to extrapolate this evolutionary process into the local scale of a slope. In a very simplified scheme, we can consider the water table's progressive rise after a temporal horizon influenced by anthropogenic global warming and the evolution of hydric balance. In this case, we are adopting a scenario where the new IDF, driven by anthropogenic global warming, will cause a higher amount of rainfall and therefore an over-recharge of the aquifers and the raise of the water tables, followed by a progressive increase in interstitial pressure, and in this case, in a cohesive soil under undrained conditions. So here we might have the current water table at rest for a safety factor of higher than 1. Eventually, we will have a critical water table leading to an eventual slope failure with a safety factor lower than 1. And here we will have the potential surface of failure. Here are the heads estimated, the values of interstitial pressure estimated for any point on any equipotential of the aquifer associated for the state of stress and deformation that might reign under this scenario. So the difference between the position of the water table at rest and that of the critical condition will progressively be reduced, and therefore a smaller return period of rainfall will be required to reach the state of rupture. This difference will therefore be progressively smaller and smaller through time under the scenario where the IDF will associated to anthropogenic global warming will be higher, larger than the one originally produced. By means of a heuristic model, and after all of what has been discussed previously, it is possible to analyze what could happen in slopes under the possible future influence of anthropogenic global warming. Slope and stability hazard, as proposed by the Mora-Varsno method, is composed by two main parameters: susceptibility and trigger. Susceptibility describes the intrinsic slope susceptibility, and it is composed by the indicator of relief or geometry of the slope, angle, relative relief, and any other indicator that might be valuable. The indicator of the lithological susceptibility, which is a proxy of shear strength obtained by perception or determination. And the indicator of ground moisture content, we call it the prevalent ground moisture, is the ground moisture content that is waiting for the big rainfall to come. And there, the trigger parameters that describe the influence of external trigger factors, such as, in this case, seismicity, described by its intensity, and precipitation, described by IDF functions of rainfall. So the slope and stability hazard might be determined by a combination of relief, lithology, moisture, combined by seismicity and precipitation. This model requires an iterative calibration as knowledge of the slope and stability inventory and trigger mechanisms improve. So anthropogenic global warming under the scenario we are analyzing will influence two main parameters: the ground moisture content and the influence of rainfall. Following the preceding notions, an actual application has been performed in the municipality of Esparza in Costa Rica, where data is very scarce and where it was required to produce a model to orient land use planning in the middle term. Amongst the analysis carried out, there was an attempt to assess the possible future changes in slope and stability hazard. We can see here a map depicting the current slope and stability intensity and spatial distribution of the hazard situation. And after applying the increment of, in this case, 10% of the IDF function that we described earlier in this presentation, a scenario on how this situation might evolve in a, let's say, approximately 50 years of temporal horizon. As you can see, there is an increment on the red areas, the pink areas, and for example, the appearance of hazard, let's say significant hazard in cliffs and other slope areas. Once a rational scenario is produced, risk management can be guided by a series of decision-making considerations and options to face slope and stability hazards influenced by anthropogenic global warming and after a temporal horizon of 30, 50 or more years. Scenarios must become the product of probabilistic exercises, but once robust models can be applied, fed with adequate hydrometeorological and geotechnical data and analytical procedures. Meanwhile, decision makers can be provided with at least general prognosis guideline options with recommendations for structural and non-structural measures. Remember, structural measures, we refer to engineering, corrective measures such as, for example, slope stability works under adjustment, drainage, erosion control and revegetation, protection against sea level rise. The non-structural measures, which are prospective, are essentially composed by land use, territorial planning, the reduction of vulnerability, retention, transfer, and risk financing, improve environmental natural resources and watershed management, emergency and disaster management improvement, and social and business operative and functional continuity. And there is a third option, not take actions. If this is the choice of the decision makers, we must ask them if they understand the difference between accepted and acceptable risk, and if this difference is tolerable, if there are any contingent liabilities remaining, if there is a partial or a total coverage for damages and losses to come, and warn them that they must be aware of residual risk and social responsibility. So, to conclude and recommend, to assess the influence of the anthropogenic global warming to slope and stability hazards, this is a task that appears far from being simple. It is instead a very complex job. It is indeed a multivariable process where relations between factors are not always well documented and understood. Scarcity of data and information in developing countries prevent from having robust calculations, probabilistic modeling, scenario building, and manageable uncertainties. It is necessary and possible to apply transient temporal instruments and heuristic simplified deterministic procedures before advancing towards a more complex methodologies to orient decision-making under the conditions of making that the appropriate data and factors are included in the analysis. Analytical scenarios producing prognosis and engineering judgment apply to assess the influence of enhanced extremes of the climate variability and the evolution of local hydric balances and the influence of slope and stability are necessary, even if sometimes they might become rather schematic. Downscaling global models do not yet have sufficient spatial resolution. They must be reinforced and recalibrated with local data to refine scenarios through specific temporal horizons. Analyzing the variations and evolution of human vulnerability and environmental conditions is essential by means of projections of the eventual socioeconomic and environmental effects, impacts, damage, and losses. Financial engineering models must be able to compare decision-making scenarios, such as actions taken, but versus limited actions taken versus inaction. And then use benefit cost ratios, net added values, and other economic metrics and parameters to make the rational comparisons. Risk management measures, prevention and mitigation, structural and non-structural, must be dynamic and adaptable to face at least any foreseeable situation. Unfortunately, risk management derived from slope instability hazard is still not a priority in many countries, since it is seen as a cost, not as an investment. And therefore, climate change will continue to be blamed only for future disasters. Muchas gracias.
Thank you very much, Sergio, for this excellent and comprehensive presentation on this very complex subject that is affecting us, at least here in Colombia. I can speak from Colombia. This is a very relevant subject. The Geological Survey has been doing a very detailed and intense work on the evaluation of the hazard because of landslides in Colombia for many years now. But we see that, as you have mentioned very clearly, that these models now need to be evolutionary models that will take into account these changes that are occurring in the climate, in global, because of global warming and some other things. Here in Colombia, I would say that we are going through a process of large scale construction of roads, particularly, including a number of tunnels and very large slopes. Also some large projects, particular projects, infrastructure projects or development that have had recently serious problems because of these unforeseen conditions, particularly during construction, with the changes in the rainfall and water conditions that in these tropical and active tectonic settings that we have imply very complex geologies and geological conditions and hydrogeological conditions and so on. And we have seen many situations that during construction there has been worse scenarios being occurring than actually what has been considered for long-term design of the projects, and have had serious problems with the landslides, with the interruption of key roads here in the country, several conditions, several cases, and so on. So also the vulnerability of the slopes has been increased because of the construction of shallow tunnels, for example, or very large scale cuts for slopes, roads. So it's not only that we have to plan on that, but we have to deal with that right now. And I agree with you that that's something that is not taken seriously enough, at least in our countries, and is taking a lot of high cost. So I thank you very much for your excellent presentation and your call for us to take into account these problems and be working on that. I can remind you that you can do your questions on the chat, please. I have a question from John Grajales that says, thanks, Dr. Mora. I like to know, how would you address time variability in geomechanical parameters according to the projection of 30, 50, 100 years? Please, just an idea, I think.
That's it. That's a $1 million question. Yeah, I wish I could offer a definite answer, but I could say I have thought about this. Is essentially the answer might be on the way materials, surface materials or ground materials in slopes may vary through time as exposed to weathering, for example, or exposed to moisture and chemical agents and the changes in anthropogenic activity as well. So geomechanical properties of slope grounds and materials terrains may vary effectively. And the velocity of variation might depend on the physical, mechanical, and chemical composition of those materials. So perhaps a granite will not vary as much as a shale or residual soil that might become more oxidized and perhaps change its geomechanical properties along the time. As for anything else, I don't have any other possibility or any other measure is impossible because we're just starting to analyze, and we have to check better and perhaps even produce laboratory tests and observations in the field.
Thank you, Sergio. I have another question from Gloria Lucia Ruiz. Dr. Mora, asks Dr. Mora, that kind of risk assessment, to what scale is applicable?
Well, risk might be risk assessment can be applied to any scale. It depends on what you are trying to assess. You can assess countries. Actually, Colombia is one of the cornerstones and the crib of risk assessment in Latin America and the world. Let's talk about CAPRA and other platforms derived at the University in Manizales, Omar Darío Cardona, and so on. And it means that you can analyze a country, and then you can analyze a region or even a particular site. It depends on the resolution and the precision of the information and data that you have at your disposal.
Okay, I have another intervention. This is from Álvaro González. He says, excellent presentation. Do you have a special software for these evaluations?
No, not yet. We can use, as I mentioned, CAPRA platforms of the kind, and perhaps you can add the sequence, an additional algorithm or whatever, but this is up to my knowledge, there are no software available for that yet.
So far we have to deal with the problem as it comes with whatever we have at hand.
But this is a very seminal presentation of concepts and notions.
Yeah.
Perhaps I hope this will spur the creativity of people that are perhaps more into that kind of fields of expertise.
Right. I think something which is very important is we have to have clear the concept to begin with, and that's
Yes.
That's a very important contribution what you are doing on that regard. Okay, I have a question here from Dave Pesley. Says, in very high mountain areas, anthropogenic warming is usually amplified, sometimes by 3 times or more. How can we quantify the increased hazard of large rock slope failures associated with the complex processes of permafrost degradation, which lead to these very large failures?
Okay, I have more focused my my analysis on tropical and subtropical areas, and there are some high mountains and areas with glaciers and snow, but I don't remember in Latin America any permafrost area. So I will not venture on offering an opinion that it is not under my field of expertise. However, my first recommendation will be to make sure that this change is due to anthropogenic global warming and separated from natural climate change and climate variability. So there is a lot of discussion. I know that evidences are heavy in terms of the anthropogenically driven changes in climate, but not everything is still well explained and quantified. So I would expect that essentially the change of permafrost, the change in the conditions in high mountains will come perhaps at a higher rate of development than other areas. But I cannot offer any further opinion to that respect.
Thank you. Silvana says, in general, do you think landslides are considered as relevant or discussed in the same way as other natural disasters, such as flood, droughts, even wildfires? If not, how we can redirect the look to landslides from organizations such as IPCC? Thank you for your great presentation.
I believe that we took the example of slope instability because it's the field where I have worked mostly, but I guess the other hazards can also be assessed in a similar way. Of course, taking all proportions and parameters into account, but I believe that yes, since anthropogenic global warming acts in particular areas and modifies first microclimates, which are perhaps more susceptible and ready to change. They are borderline in the change. Perhaps it could happen that drought and fires and floods could also be analyzed in such a way. I believe that it is also a topic to be developed by specialists.
Okay. Have another intervention here. It's from Adriana Talamini, UFPR. Says, thanks, Dr. Mora, for your excellent presentation. What kind of monitoring systems you would recommend for access risk considering this approach?
Well, it's also a tough question because one thing that we have to realize is that we cannot analyze twice a failed slope because it will not be the same slope, and because, for example, if we install a piezometer or a geodetic device to assess deformation and the changes in the state of stress and hydrogeological conditions, if the slope fails, we will lose the baseline, and then we have a new slope to assess and start over. So it will take time to accommodate a process to be able to assess this in a statistical way. However, the first evidences might come from the fact that if we have sufficiently long time series of, for example, water level readings and geotechnical, geomechanical characterizations of slopes, and if we have sufficient resolution to measure these small changes through time, we're talking about several years, we can have at least trends that might lead us to prove and to ascertain that these evolutionary processes may actually and really occur. But it will depend on the long-term measures, geomechanical, geotechnical measures, and very closely associated to hydrometeorological instruments as well.
Okay. We have time for probably one or two more questions. I don't have any at this time in the chat. If anybody wants to do another question, please do it now to be wrapping up the session. So So really, I really believe that we have a lot of work to do to understand and quantify better our processes, instability processes, hydrogeological processes, etc. And we have to be very careful on in the way how we deal with the construction projects, the development, the planning, etc. Because we are facing undoubtedly an increase in the risk, particularly here in our tropical countries where water is not getting lower, it's getting higher. It's getting more and more. So, and that's something that really affects the slopes. So, I hope we will